Yeah, so this is kind of a part 2 of the discussion we had a few weeks ago about how we might speed up some of the slower computations in Monty. And yeah, just as a short reminder, last time I showed this kind of analysis of which functions take about how long to run at the moment. And we talked a lot about KDTreeSearch and kind of possible alternatives for that. And then I also went over some of the matrix multiplications and other matrix operations that we are using. But yeah, we didn't have that much time to talk about that. And so I thought I'll start off with those. So it looks like the KDTreeSearch is the biggest thing to look at, but all these matrix operations actually add up to quite a bit as well. And the thing is that we can probably apply, if there is some way to speed them up, we can probably apply it to all of these. So I just thought it could be worth it to look at that a bit more.
How did we end up on the tree search? I remember we had the suggestion to do a table lookup, but then that didn't sound like it was going to work. Where did we end up on?
Yeah, so the table lookup does speed up the search during inference. The problem is it slows down, like the building of the table takes a long time. So if we are just focusing on speeding up inference, it's definitely a viable option. But if we kind of want to keep the option of being able to learn continuously fast and being able to update our models often, then it's probably not the best solution. So
does it provide any advantage in there, or it's actually worse?
Yeah, for updating, it's actually worse.
I mean, so overall, it's not a good idea. Okay, well, that's unfortunate. So all that didn't get anywhere. Okay. All right, next, now we're looking at the next best option.
Yeah, I mean, at some point it might be good to go back again to the KD tree and dive into it at some point. But yeah, the table lookup is really just an inference thing, I think.
Yeah, so I found another paper that looked kind of promising. They use a special way to search octrees, I think they use, that is especially optimized for searching 3D point clouds, which is exactly what we're doing. So I might have a closer look at that one, but unfortunately they don't have any code online, so it would be a bit of a longer time commitment to try that one out. But yeah, there might be some other alternatives to the KDTreeSearch.
As for spatial queries, like I think it's like R-trees or something.
Their implementation, you mean?
Yeah, I think that's something used for a spatial database, like R-trees. I think I've seen this R-tree stuff.
Yeah, I'm not 100% sure about what they do. They somehow like sort it in a specific way that it's really quick to search through. I mean, which is also done in KDTree, but apparently it's optimized for 3D point clouds. So
yeah, there are some
I would have to
PVH bounding value hierarchy, like they chunk them in terms of like bounding boxes, and then they divide amongst those.
That's what I remember as well, like something like that. Like that was used for databases. I don't know if that's also used for that.
Yeah. So, but yeah. Sorry?
Well, so I've seen that used in GIS systems, like in spatial databases.
Yeah, that's what I've seen as well.
So there must be some open source.
Oh, absolutely. There is, like Postgres has it.
Right. I guess it would be good if there was Python bindings.
There's a Python version of that. Okay.
I'm sorry.
Can you share the link of that?
I'll look this before Numenta, that's before my Numenta.
I'll see if I can find it.
By my new pen, that's a long time ago.
Maybe you know the keywords to search for.
Yeah, R3s, OCT3s, that was a keyword that brought it. R3s for the GIS systems. They have
ARC.
R-3.
Oh, R.
I think that's what's the name.
And this is related
Is
to
that the GIS system, right?
Yeah,
yeah.
R3GIS.com, but that's a company. I think.
No, but I think there's a three.
I'm sorry, is this related to the matrix operations? or
That's the KDTreeSearch.
That's for. I forgot.
Okay, we can look this up.
But it's the GIS technique is for searching. As exactly as the Eric was describing, it's just they create a tree of spaces that you can find within the space.
Okay. All right, yeah, so yeah, I'll have a look at that, but yeah, at least for now, kind of the conclusion here was that we'll wait with implementing something because we don't want to over optimize for inference right now, and kind of keep it flexible to be fast also for model updating. And then, but the matrix operations might still be a viable thing to add speed ups, and that would not be the biggest computation to be removed, but still a significant chunk of computations that could be sped up. So I'm not going to go into the exact applications of these again and where we use these operations, but generally just a collection of, here's again the collection of operations that we apply. And the main point is that right now we always do the full matrix operation on all of the hypotheses. We update every hypothesis at every step, but in practice, we don't really need to test all hypotheses at every time step. We could just test the most likely ones. And that way we could mask a lot of the rows in the first axis. So along like where I put H as the shape, which can be between 1,000 and 40,000 rows. And then the second one, some entries in K are also already masked since some locations in space have less than K neighbors in the allowed radius. So those could also be masked. So overall, we have, for example, here when we do the dot product, we have a big matrix of size H times K times 3, but almost all of the rows could be ignored. Some of the columns could be ignored in those rows. And then, yeah, obviously the third dimension is also ignored if a row is ignored. So the question would just be if there's some efficient way we could make use of this fact that we can actually ignore a lot of the rows and in every step.
So if one thing that comes to mind is if you can somehow sort these hypotheses so they're all together, then you can just do brute force on that subset. But then of course you have the cost of the sorting operation. But so that would be one possibility, is if you could just stack them up so all the white ones are at the top, and then just do those. But do you think there's a lot of change in the top few hypotheses if you were to sort it? Because if it's compute, it's intensive to sort it, but then updating it could be pretty easy.
Yeah, I mean, there definitely is change in the top K hypotheses, but after a few steps, it gets kind of stable, depending on at how many hypotheses you look at. So if it's just the top 10 or something, then it gets pretty stable after several steps, but it can still change depending on how you move over the object and when you see significant features.
Right, and if it changes and you didn't have that in your top 10, then would also fail then? I mean, it's possible it just might not recognize it like that. I mean,
it would just mean that a different row is now grayed out and a different row is now needs to be updated now. So if we had sorted it,
whether if it's stable, then you don't have to worry about doing that sort and unsort again, or
or it can be much faster to update it. It's
right.
much faster than to resort the whole thing. But you definitely want to do all of the white ones.
Yeah, no, I know,
Yeah.
but I'm saying, but if the set of winners is changing over time, then if you don't update it, then you're gonna miss that, right?
Right. So you want a fast update. That's what I was.
Yeah.
It's faster to sort into a already sorted list than it is to sort from a random list.
Okay,
Yeah.
all right, okay, thank you. That might help us.
And yeah, if we sort it, we still want to keep like a reference indexing between like which row used to correspond to what hypothesis, basically.
Yeah. I know in our old sparse matrix stuff, I think every row was like a pointer.
We have a
So you
pointer
could, reorder them very easily. But I don't know.
in the
I'm getting something.
rightmost, right,
Yeah.
right thing. I think in the new implementation, if I remember correctly, in the columns, I think Marcus did something with PyTorch. So
Yeah, that was Abi.
that was Abby.
Yeah.
I was able to do something similar with PyTorch. So maybe we can, but we just moved PyTorch from the brother, so. We just moved PyTorch from Monty, so I don't know if we can do that.
But I think Marcus's one probably, I don't know if it used pointers for each row.
He used pointers.
He used pointers.
Yeah.
Then it's very easy to resort.
Yeah, he used pointers. Every row was a pointer.
So yeah, I guess the question is it faster to sort this thing and then take only the top ones to multiply, or would it actually be better to just try and move the implementation onto GPUs and do the large matrix multiplications?
Well, we could, so two questions there. One is, if you could sort it, I mean, sorting 10,000 should be super fast. Then once you sort it, then that matrix structure, you can use all of these operations on that. So it's not like you have to resort it for each one. You just have to resort it when your hypotheses change, which is the bigger loop. So internally, once you sort it, you can just do everything here with that structure.
Yeah.
In terms of GPU, I don't know, GPUs will be very fast at it, but then you have to worry about data going back and forth between the data, between GPU and CPU constantly. So I don't know how that would play out. Yeah, thoughts on that?
Usually that's a bad idea.
Yeah.
I mean, if once you get on the GPU, you want to do a lot on the GPU to amortize the cost of that data movement. So just so I understand, is we have is that 10,000? That's supposed to be the length there?
Yeah, it can be up to between 1,000 and 40,000 usually.
Okay, and what's the ranking of these things? In other words, what's the figure of merit? What's the range on that?
But what do you mean by what we would sort it, or?
Yes, yeah.
Here's the R3. Looks like.
So that would be the amount of evidence for each of the rows, basically, and the evidence can either be bound to, for example, to be between -1 and 1, or it can be arbitrary, so it can like grow infinitely.
Okay, but I'm see if I can ask this a different way. If let's say it was quantized, let's say arbitrarily, you only have 10 values that the hypothesis validity can fall into. Would that severely compromise what you're doing here, or do you need to define level precision so that these things actually filter out to a very fine cream on the top sort of thing?
10 might be pushing it a bit, but it should be still okay. The bigger issue is if we bound it to a range, like say -1 or 1 or like 10 bins. It basically means that we have like a time horizon of what we can remember. So we need a very efficient policy to see all the significant features in that time horizon to recognize the object. If that makes any sense.
Okay, so when you were talking about sorting, are you sorting on a scalar, or are you sorting on each of the dot products individually?
Right now we don't do any sorting. We just
If you would sort, what's
what's the algorithm to figure out the top ones that you want to keep for this operation?
Yeah, so for example, the dot product is to calculate the angular difference between hypothesis and observation. And then from that difference, we get an error, which is added to the evidence. And then we have a separate array, which is the evidence for each of these rows. And we just take the maximum of that.
Yeah, so normally it would be a scalar for basically the evidence value for each hypothesis.
Yeah.
Okay, so is the bulk of the time in doing the operation afterwards, or is it computing the evidence?
It's all of it together, like so einsam, this is the top one. This is computing the dot product between the angle difference.
Right.
But then there are also some other operations like computing the difference between observed features, getting distances, and yeah, just like weighing the evidence by however much we want to weigh each feature.
Okay, let me be more specific. You have some amount of calculation to come up with that scalar, which hypothetically, if you were to sort on and then only operate on those rows which had high enough evidence, or all of them that had some, greater than threshold evidence, I'm trying to figure out the how much of the processing is split between arriving at that estimate of the evidence and then actually processing the rows once you have the evidence.
Yeah, I would say basically all of these are used for arriving at the evidence values, except for this one, if I remember right, corresponds to the maximum. So getting the most likely hypothesis out of there.
Okay, so
then it wouldn't help too much.
yeah, exactly. Because I was going to say, if you get down to an evidence number, and you let's make it a say 256 evidence levels. Let's suppose you mapped into that. Then you can use a bin sort, and those are really fast because you basically index on that evidence and just put it into a list. But if you're spending the bulk of your time coming to that point, then it's kind of moot.
Well, no, that would be done.
But it would be a lot quicker, yeah.
Step. So we would have the evidence from the previous time step, and then we only want to do all these operations on the top K ones.
Okay.
Oh, okay. Yeah, so let me.
At the very first time step, we would have to do all of these, but then after that, we can just take the top K evidence values from the previous time step and update those with the new observation.
I see.
Okay, so if that were the case, I mean, you can do bin sort in linear time. So that would allow you to at least bucket them.
Will we actually need to sort the entire array, or if we just need the top K, could we just stop?
Well, that's why you see. That's why I was looking at what makes it white, what makes it gray.
Mm-hmm.
If you know ahead of time where the white ones are, then it's moot. If those gray ones are potentials that just didn't fall into a large enough, quartile or quintile, whatever of the things, then that's a different question.
Yeah.
So yeah, what you might do is think about have like a threshold, like a dividing line between, what is good evidence and what is bad evidence, and just sort of sort them into two bins. So after say the first iteration, you're maybe at 50%, maybe after the second iteration, you're at 75, and then 80 or whatever, and you can just continue to close that gap, and you should see less and less of them showing up with a high enough thing, so that you can just concentrate on those that are exceeding the threshold amount of evidence.
Well, the problem is that their threshold is not going to be constant. So what we did in
That's what I'm saying, yeah.
K-winners
The
on
more
the
evidence you
FPGA,
gain,
what we did on the K-winners of the FPGA was that we did one pass through to form a histogram, processed the histogram to find where the threshold was, and then did a second pass through, picking off the ones that are greater than threshold.
Yeah, it's kind of similar to what we do with the voting at the moment. Basically, we scale the votes to be in a range of -1 to 1 by using the maximum and minimum value. And then we just set like a fixed threshold. It has to be like above 0.8, so like in the top 10% percentile. So we could do
Yeah.
something similar here. It doesn't have to be like a fixed number of n rows that we look at. It can just be
Yeah,
above.
I mean, there are advantages in getting away from a bounded floating point range to a bounded integer range, because then you can do addressing operations based upon the integer values or lookups or a variety of other things. As a floating point value, then you're stuck with kind of doing comparisons all the way through.
whereas if you're just doing binning, like you're just like storing the index of the hypothesis in one bin being greater than threshold and one bin being less than threshold, then you don't have to do any sorting. You're just basically just binning them into one or the other.
Okay.
And how do you create this big matrix? Is this, you create it once and then I'm just wondering how this matrix evolves. Does it always get smaller?
No.
Is it you recreate it every time?
Yeah, it's always the same. So this is constant. This is all the hypotheses that we have, and then we use the this is constant. This is all the hypotheses we have, and then this is using the observation and the k-nearest neighbors of this location, and comparing that basically to the stored features in the graph.
So with every new sample, with every new sensation, you have to recreate that HK3 matrix?
Yes.
Okay. But H is at least fixed.
Yeah, so yeah, H is a fixed size. It's always the same from the start of an episode. And then we basically have to find the k-nearest neighbors of the location in the graph and take the features stored there, which are unit vectors in 3D space, so 3. And then we have to take the observed vector and rotate it by the hypothesized poses, which might be different for each of the rows. And then this is that.
Is there any way you could just, do some algorithm, either sort or what Kevin was saying, just to pick the white hypotheses, and then only create the matrices for those white rows? Then you don't have any gray elements, any gray rows.
Yeah, we could. That's true. We could only, like, basically H would be variable then here, and it would be much smaller.
Yeah.
Yeah, that would actually be the
think I
easiest
can help.
way to do it.
I don't think I can help, so I'm gonna go do something.
You can optimize your time.
I'm on to it.
Yeah, sorry about that.
No apologies.
Yeah, I mean, if that works, then you could just keep everything else the same. It's just you have an H prime, which is the top set that's right now. And then
But that works for the second and third, not for the first step. First step, we still have the 10 time.
no, everything would be with H prime once you sort it.
No, but the first step, we don't know what the whites are.
The first step, yeah. Well,
Yeah.
once you do though.
So, and then we would just have to keep like a some kind of reference to which hypotheses the white rows then refer to, basically.
Yeah.
And the number should go down with each iteration. You should have less and less.
Yeah.
Yeah, you should have less and less, and it should go super fast. Point.
I mean, the only time this will cause problems is when you've got noise in the data and you might be discounting hypotheses prematurely because the data was noisy. But that's something that could be an optimization on a later pass.
Yeah, well, we can always come back to any of the gray rows if the white ones become less likely because the evidence we see is inconsistent with it, then we'll come back to older hypotheses. It would just take longer to get there than it would if we update the whole matrix, in theory.
We've also kind of been talking about kind of adding some sort of resampling process to kind of reconsider less likely ones. And if we have this kind of sparse subset of most likely ones, we could also kind of use that extra budget to kind of add in like low probability ones every now and then, kind of resample them.
Boosting.
Okay, yeah, I'll have to think and go through the code to see if that would be an easy change to make it. Right now, it sounds like it should be possible to just, before even creating these matrices, we select by the highest evidence values and then just keep a reference to which they correspond to.
And yeah, in terms of what you were saying, Kevin, so would the fastest be firstly like a hard threshold, just like, because yeah, we could have a variable threshold based on how much evidence we'd accumulated or whatever. But then like an arbitrary number of k, specifically the sorting bit, would that be faster, or would like having sorting the top k, presumably that would be slower?
I'm sorry, what was the second one again?
Like specifically looking for like say the top 100, or specifically looking for like any that are above a fixed threshold?
I would say, because you don't know, if you wish, ahead of time what your confidence on all this stuff is going to be, what the range is, you might want to basically pick your strongest ones. I mean, you could use heuristics on this thing. If you're getting a bunch of hypotheses and then there's all of a sudden a drop off in what I would call confidence, then you might threshold at that point. But the point of it is to bring all these things into a metric, if you wish, that allows you to make that choice. Typically, if anything where you can something becomes a fixed k, makes it easier, because then all your subsequent array allocations and everything else, your loops, all of them become fixed. But it really depends upon how your data works, how it distributes, how it evolves as you get each additional sensation. So I don't know ahead of time, what the dynamics of that would be. But I think, I mean, what you were talking about earlier, which is I was actually thinking about recommending, is that if you do come up with some threshold that's derived by whatever heuristic, that the ones that fail by a small amount, you might want to reserve off to the side, as filtering in, just like you were talking about, because that's essentially how we work with K winners. Is when during training, we don't want things to fall off all the way off if they happen to just once, during training, fall below threshold, because then they're forever lost. So part of the boosting algorithm is to resurface those guys, kind of give them, is say, okay, here's what your figure merit was, but we'll give you an extra 10%. And does that bring you above threshold? Okay, we'll try you again, and kind of randomly sort through there. So it gives you the ability to, if you wish, have a memory and re-examine these things if the context changes. I mean, there could be something that's way out of band that would be, that was just deselected in the beginning. That forever, if this thing is like, highly non-Lipschitz, there's something wild that could come out, then nothing's going to work on that. But I think the hope is that you're in a space that is that is relatively smooth and relatively progressive toward and converging toward a solution. And if you can establish, some criteria or some heuristic to say, hey, if we work with, up to a certain threshold based upon some heuristic, they will reserve 10% more off on the side to on the off chance that things are getting worse, to kind of filter them in randomly. So you're not, so you have K plus some delta of that reserve pool to play with. If you have an assorted list, then you basically can play those games and assume that, the degree of the confidence you have there is also proportional to the likelihood that they could be a viable candidate, then play all those games.
Okay, thanks. And then and the thing about the kind of integer values rather than floating points. So do you think, well, yeah, I guess would that still apply if we were doing the threshold? And I guess would Python, I wasn't sure the reason you gave for like,
Well,
that helps or whatever.
it depends upon what you're doing. If you're
If we're not actually storing the list or like specifically calling.
right. So if you're not specifically sorting it, then it might not be as interesting. However, if you basically have a threshold and you wanted some place to say, okay, where do I put these rows? I've got these rows. What's the data structure that I put them into? And I would still like them to have kind of be in priority order, I would think. I would think that you would want to try the most likely ones first. Am I incorrect, or are you going to try them all equally?
I mean, at the moment we try them all equally, but yeah.
Okay.
Yeah, even if we threshold, we would want to update all of the ones that are above the threshold or in the top K.
Right. So the advantage of quantizing that value, it doesn't have to be as fine as I mentioned. I was just using that as a as a straw man. But if you want to deal with these things as groups, where you store them as, if you wish, clusters, physically they can then reside at some point in near values in memory, so that you're not, so that if you're on a CPU, you're not randomly accessing memory all over the place. You might want to migrate those rows into physically adjacent storage, just for the purposes of the fact when you bring in one of these guys, you could drag in the memory for the next couple of, and your memory cache efficiency goes up.
Yeah, that's actually a good idea.
That's a second order effect, but basically having a quantized address or tag or where to look for these things makes it easier to just use a lookup table and says, oh, okay, I'm looking for cluster 5, lookup table, okay, memory location, this bounded by this, go and do those things. I'm just saying that, it really depends. If you're going to look at all of them equally, you're going to do the same thing as well. But if they're scattered all across memory, you're going to pay costs for that. There are advantages in bringing things close together in memory.
And would we have that flexibility in Python, or is there a way to kind of?
Well, I mean, you basically, I mean, you have a maximum size of what the row can be. That's your K is equal to 10, right? So you allocate an array of n cells, okay? And then once you process it the first time, you might, allocate some subsidiary arrays, K is equal to 10, H equal to, I don't know, 20, something. I mean, I could do the computations for you to figure out what would fit into L1, L2 cache, that kind of stuff. But the thing is that if you're going to bring these guys in and maybe re-access them multiple times in quick succession, then there's an advantage in keeping them in close memory, if you wish, nearby memory, So again, this is a
this all assumes a C implementation, not a Python.
You can still do it that way. I mean, it's just an array.
Python will blow any cache comparison you have. The whole interpreter running for every line of code.
In the memory access pattern, though, it's still going to be coherent. I mean, the instruction cache, yes, but the data cache, if they're basically accessing coherent rows, that can't help but be benefit. I mean, that's the underlying machine architecture.
No, I understand. I mean, you may be right. I'm so skeptical of Python.
Well, okay.
How many clock cycles does it take to add two variables together in A plus B in Python?
If they are not using SIMD, I understand what you're saying.
It's over 100.
Yeah.
It has to do all these up. It doesn't. The plus operator might be overridden. A is a class, and everything. I mean, it's just interprets so dynamic and flexible that it's doing so much stuff. It's not like C.
So even if the underlying arrays were NumPy, they still have all these characteristics,
No, a NumPy operation is optimized,
right?
but in between them, in between lines of Python, like
Right.
NumPy, it could just completely blow the cache.
Okay.
That's what I don't know. That's my suspicion.
Okay. So what Subutai's right. I'm basically mapping this onto a C++ model where the operations you want to pare them down to the most efficient things possible. So
I mean, you might be right too. I mean, it might.
Yeah.
If they do try to optimize.
We would
that.
have to profile to see whether you are compute intensive or whether you're memory intensive on this. And if Subutai's hypothesis is correct, if you're compute intensive, what I'm talking about would be a second order effect on top of everything else.
Yeah, right.
So
Yeah, no, that sounds interesting though. And yeah, thanks. I definitely think one day we'll hopefully have a lot of this re-implemented in C anyways, so.
well, I didn't know whether you guys were there yet with this meeting. So.
Not yet.
Okay, all
I have a
right.
quick question. Just to refresh my memory, it's like the things that you're using to judge whether an observation matches with a hypothesis. What does that feature vector look like? Just real quick. Is it just like normals and tangents or something? What is the features that you're comparing observations against hypotheses?
We have two different types so we have features like color and yeah, just features that don't change when the object rotates, and that's just an array of numbers. And then we have the point normals and curvature directions, which are like these matrices that have threes in here, that are basically unit vectors.
So which ones are you using to compare in this this dot product Einstein matrix? What are the values of the three values, the dimension that you're collapsing in these products? What is that? What are the values that are being multiplied there?
Here we take the dot product basically between the observed rotated.
I think he's asking, is it X, Y, Z?
Anomaly.
He's asking if it's X, Y, Z.
What are those values? What do they correspond to? Are they rotations? Are they positions? What are they?
Oh yeah, it's XYZ coordinates of a unit vector.
Okay. So it's a normal.
Yeah.
Okay. All right. So then there's a very easy way basically to speed this up, and that is basically sort your entries in that matrix, the H matrix, sort them along the lines of their orientation, basically, so that when you bring in an observation and it's obviously pointing in this direction, if you have like the list is already sorted on those hypotheses, like those orientations, then you can go directly to the part in the list where you've got everything that's oriented in that direction. Or do you have to do another transformation to see?
No, they can't sort because they have multiple. That's a matrix there. That's a 3x matrix.
Right.
So you can't. So you have multiple orientations you're going against.
Okay. So
they have to perform the entire dot product there, and then do whatever processing they do to say, okay, this is representative of a good fit.
All right, so for each hypothesis, you've got 10 possible neighbors, right? So that there's like points that you could move to nearby and their orientations, right?
Yeah.
Is there any way that you can sort those based on what the observation is?
I guess we could, but we still have to calculate them all because we also want to get the negative evidence if it doesn't match.
Okay, all right. All right, never mind. I was just thinking that there might be a way that you could orient or organize the hypotheses and those k nearest neighbors in such a way that you could very quickly go to the ones that were closely aligned with the observation that you're bringing in, given that they're both in these three-dimensional spaces.
Yeah.
All right, never mind. It was just a thought.
Yeah. So I think I'll try doing what Subutai suggested, to just threshold before even building these matrices, see if there's something I'm not thinking about right now why it doesn't work, and then can look into that some more as well. But if that works, that would save us a lot of time also with the KDTreeSearch, because we wouldn't have to even search for a lot of the hypotheses nearest neighbors. So let's see. Then
that could be interesting.
Yeah, that would be a cool side effect.
So the big question for you is deciding how to arrive at that threshold. Whether it's a fixed one or a dynamic one. If it's dynamic, is it based upon you're falling off on the level of evidence, or is it something else? So that's the real trick in any of those things, is the heuristic to figure out what's a principled threshold.
Yeah,
because we could save a lot of computation if we ended up essentially kind of ignoring objects that are extremely low evidence, and like those were having almost no point updates.
Yeah, that would be even a second threshold, to just not do any update for a whole object.
If it just doesn't
slow. Yeah. I have another topic. I don't know if.
We could do that. By the way, these are all sort of these lazy person optimizations, which are, rather than doing something faster, avoid doing it at all.
Yes.
Tried it through a true optimization technique.
Yeah.
Fastest computation is the one you don't have to do.
Exactly. Yeah.
Just have to prioritize here.
Yeah.
So the second topic, I don't know if there is a good solution to it in Python or not, but I was just wondering if anyone knows about better alternatives to multithreading. So I don't know if you remember from last time, but we do multiprocessing across episodes. So we do that, but then within these processes, we also do multithreading over objects, because we can update each object's evidence independently of all the other objects. And for that, we use Python's threading.thread, but it gives us only about a 2 to 3x speedup. And theoretically, we would want the speedup to be proportional to the number of objects in memory. So a 77x speedup for the YCB dataset, for example, but it isn't. So for example,
So you're saying you're doing multi-processing over episodes. So each episode is in a separate process?
Yeah.
And
during inference.
Or thread, there's two different things.
Yeah, so every episode is in its own process, and then for each episode you want to use threads to do that, right?
Yeah. So basically, here episodes are parallelized during evaluation. During training, we can't do that because they have to be in order. But then, within the episode, basically for this for loop for object in memory, we run each update evidence call in a step in using Python multi-threading. But it still doesn't seem to give as much speed up as it should. And for example, during the demo, you saw it seemed quite fast. But that was because we only had 9 objects in memory. And then when we have 77 objects in memory, it's basically a linear multiplier, however many objects you have in memory.
Yeah, it's not going to help much because if your processes are all busy, assuming they're using up the compute, I mean, multi-threading will only help if there's spare CPUs lying around.
Yeah, and you're also thrashing your cache, with all those objects, you're in memory. Yeah, you're swapping back out from memory, but you're also ejecting from cache quite frequently.
Yeah,
If they're sharing the same processor, I guess.
so I'm not sure how, I just say up front, I'm not sure how Python implements threading. Because I always, I used to be told that it was a single threaded process. You had to do something extraordinary to get to multi-threading. So I'm not sure what type of threading is going on here. But having said that, if I wasn't in Python, there's this notion of affinity where you basically lock a process to a particular CPU. And then it doesn't help you to do more than 2 threads on that CPU because there's only hardware support for 2 threads.
Mhm.
And the only time it switches is either you yield it or it has to do an IO operation that kicks off to something else. Now, the reason why you want to kind of segment it like that is because each processor, each CPU has its own L1 and L2 cache, but they all mutually share a L3 cache. So if there's 1,000 threads waiting to be run, there's no coherency there. They're basically, you're going to bring in an object and do a little bit of processing on it, kicks over to another thread because it, by whatever thing, timeout or whatever, then it's got to load that data in and do a little bit of processing on it. So you can really easily, without thinking about it, as Eric was saying, thrash the cache because you haven't really controlled how much work you're doing. For every unit of memory that you read in, are you getting a good benefit for doing that? Are you getting enough work on that? Or is it just doing a little bit and then having to be eject? And there's a double cost for that. Not only do you have to bring in the new memory, but it's got to write out the old memory right then before it does that effectively. I mean, some of it can be in parallel. So, like I said upfront, I'm not sure about what the principled way of using threading under Python is, but what I described is pretty much an optimal way of doing it. You typically don't want more than 2 threads per processor if they're all kind of doing the same thing.
Right. I mean, I know how to do this under MPI, but I don't think I've used Python threads, so I have no idea how to do it. But I know it's for using it in other parallelization modes, especially under C.
I think also, when are the threads being created? When are the thread objects being created?
Within the matching step call. So basically, I can actually show.
So the thing is, the problem to me is like the unit of work that we're trying to thread on is very small, right? It's less than this, is about a second or so, right? And if you're creating the threading objects repeatedly, spinning up new threads and then tearing them down, that's going to limit, that's a very heavyweight operation, creating and destroying threads.
Which is why people create thread pools.
Yeah. So I think that might be an issue here. It's not so bad if you're going to create them, they're going to run for 20 seconds. But the reason I think you're not seeing 77x here is that it's just too small unit of work. So what will happen is the cost of creating the thread is too high.
Okay.
So I don't know whether you can hoist the threads to the outer loop so you can establish the
that could be interesting.
Have them work.
Yeah.
Okay. Yeah.
But this is only within the episode, right? You are still seeing a 77x improvement because the episodes are parallelized. It's just within that loop you're not seeing. Is that
I don't know. I joined late and I apologize.
It
took me like an hour longer than necessary to get here because of people, roads and trees and.
Yeah, let me I think so. Yeah, definitely do what Lauren said. But I just want to I do want to understand if you're running if you're parallelizing the episodes across processes, if you have 77 objects, does it actually run roughly 77 times faster than if you ran it all on one process?
Not, unfortunately not. I think one of the reasons for that is that episodes can have very different lengths. So it will have the length of the longest episode.
Okay.
But yeah, it is definitely faster than just a 2 to 3 time speed up.
So when you spawn these processes, are you spawning them and holding on to them, or are they being also dynamically created as you need them?
Yeah, so these are basically being created and destroyed every time this matching step is called. So I guess if I understand you right, Lawrence, it would be better to just create them once at the beginning of an episode, have one thread for each object, and then keep reusing it in every step, and then only destroy them at the end.
Both the processes and the threads. I mean, forking or creating a process is an extremely heavyweight process. So typically what you want to do is create a resource of these things. And if you have the ability to know how many processors you're going to use, is if you can set the affinity to them and say, run only on this processor. Because otherwise the scheduler will it's trying to do round robin, even when you're not asking it to, and it will basically swap between processors just because. And so if you look at top K, where you can see the threads and what the processor what's running, which processor is running is jumping up and down, going over the place, because it has this aesthetic that you run for a while, and then, to be fair, let somebody else run in, unless you kind of grab hold of it and tell it not to. So again, at the Python level, I'm not sure where that is, and it certainly it's easier to do under Linux than Python running on Linux than it is under, say, Mac OS, for sure. But the whole concept of allocating these resources to particular CPUs and then mindfully subdividing that, among some subset of threads. It takes more work, it takes more thought, but you don't wind up accidentally sabotaging yourself by thrashing.
Okay. All right, yeah. So that sounds definitely like something to look into then for us.
Yeah, I mean, you have to manage your own work queues in essence. You allocate the resources and then dole them out, under your say so, rather than letting the scheduler just kind of flip a coin.
Yeah. Okay.